Hello there. In this video we're going to continue our discussion of functions, which are very extremely useful types of structures that pretty much let us save our work and let us repeat a bunch of little processes without having to write the same code over and over again. So pretty much what this function that we created in the last video is to calculate integer powers. So pretty much we can put a comment here to sort of tell whatever user is going to read this. It calculates expressions like 4.3 raised to the 4 or like negative 3.4 raised to the 8, where integer exponents only will work in this case. If you want like a fractional exponent like 0.5 to do square roots, you sort of need to go about it in a very clever way, which we'll get there eventually. So this is going to be our integer power function, and now we're going to create a new function, for example, that does factorials. So let us write it in the main function before we create a function for it, so that we know it works well. So we're going to create a new function that is going to calculate factorials, which we've already talked about in the previous videos. For example, 3 times 2 times 1 is 3 factorial, which should return a value of 6. So we're going to define an integer n, and then we're going to calculate factorial. So for int k is equal to 1, as long as k is less than or equal to m, we're going to increase the value of k by 1 each and every time. And then we're going to say, okay, well, let's define int factorial, because if we're multiplying a bunch of integers, the result is also an integer as well. And let us define f to be equal to 1 initially so we can multiply it. So f is going to be f times the value of k, and since we're multiplying by 1, we can just increase this to 2 just to save a lot of time. Right, so this is going to be the factorial value. Great. So we can see out the value, or let's ask for n. So see out n is equal to, and then we can see in the value of n, and then this loop will construct, and then we can say n factorial is equal to, and then we can see out the value of a factorial. So let's just test this just to make sure it is doing what we want. So 3 factorial is equal to 6. That's wonderful. So let's do another one. So 5 factorial is 120. So that's wonderful as well. So since this is true, that means we can write a function for the factorial now that we know how to sort of implement it. So we're going to return an integer. So it's going to be n factorial. And we're just going to input a value of n. So since we've already defined the value of n, we do not need to define anything except the answer for which we want. So int factorial, which we defined to be equal to 1 initially. And then we're just going to take this for loop that we've created, cut and paste that up here. And then we're going to return the value of factorial to the user because that's what we want to have. Alright, so we're going to delete this because it doesn't need to be defined in our program. And then we can see out the value of n factorial, the value of n that we have defined. So let's just make sure this function works appropriately. So I'm going to input the value of 3, and that returns a value of 6, which is great. And then we'll input a value of, where's my window, 5, and that gives us a value of 120, which is great. So now that we have our factorial function and our integer power function, now we can define some other functions that we may want to use. So the next function that we're going to define is actually a mathematical expression known as a Taylor series. And if you don't know what Taylor series is, that's perfectly fine. But this is going to be a very useful expression for calculating like square roots and other function expressions that we might not know how to deal with. Alright, so let us express what we call the Taylor series of a function e to the x. So remember, e, if you might not already know, is a special number like pi, which is 2.71828, and so forth. And we're not going to define that in C++ quite yet, but we're going to define or use what we call the Taylor series of x. So e to the x, if you don't already know, is going to be 1 plus x squared divided by 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus x to the 5 over 5 factorial, and so on to infinity. These terms are going to get extremely smaller as the denominator gets extremely big. So eventually we can truncate this all the way up to x to the power n divided by n factorial, where n is extremely large. And we're going to be working in for loops, so this should not make much of a difference. Alright, so let's write a for loop to sort of calculate this expression. The only thing we need to know is how to raise numbers to integer powers and also calculate factorials of numbers as well. Alright, so let us assume that we want to calculate a value for x, and keep in mind x can be anything. So let us define x. So cout, enter a value for x, and then we can cin the value for x, and then we're going to display the value of e to that number, right? So for int from k is equal to 0, and let's also define another number, int n, and let us define this number to be equal to let's start with 100. And we want this to be equal to less than or equal to that number n, and we're going to increase by k plus plus. Right? So let us also define a sum, since we're adding up a bunch of things. So this is going to be a float s, and we're going to set it to be equal to 0. So s is going to be equal to s plus. So notice that this value is going to be x to the first over 1 factorial, and this first expression is going to be x to the 0 over 0 factorial. Now this expression is going to be a little strange, but it's always going to be equal to 1. So we can actually start this at 1 and then start our k's off at 1. So the for loop is going to actually sum up this portion so we can avoid this first awkward definition of the factorial, where 0 factorial is usually defined to be equal to 0. So this is going to be equal to what? So this is going to be equal to nth power of what? So that's going to be x to the power of k divided by the factorial of the value of k that we are located at. And that's going to be equal to the sum, right? So now we can cout the value of e to the x. So e to the x is approximately equal to, and then we're going to cout the value of s, right? So to sort of test this, we know that e to the first is going to be e, and this should be equal to 2.7182818, and so on. So let's just see if this actually works for the value of x is equal to 1. So let's input 1, and that gives us 1 to the infinity. So what's going on here? Well, maybe our n is too big. So let's make n is equal to 10. Because we might be dividing by 0, so that might be an issue there. So 2.71828, so that seems pretty accurate. So how big can we get until we actually get an error here? Can it go up to 50? So let's see, 50 factorial is a little bit too large. And there are numerical mathematical ways to sort of dance around this. But 20 terms of a Taylor series should be sufficient. Okay, so let's accept that. Now there is some truncation error going on here, which we'll discuss a little bit more later, but you know, n is pretty big. That means this is sort of accurate, even though we can't see that accuracy, right? So since we are, you know, sort of confident that this may work, so you know, e to the 5th is going to be equal to that number approximately. Now we can sort of, you know, change some things with this function and actually make it a function of its own. So let's create a new function, and let's call this exp, which is usually e to the whatever. All right, so we're going to input a value of x, and let's see here. So float s is going to be equal to the number that we are going to return. So float x, and let's define this integer n to be equal to 20, and we can change this later if we really want to. So we've taken care of those things. This is the for loop that's going to calculate the value of e to that number x. And what this does is calculates e to the x via Taylor series. Right? So what is this going to be? This is going to be n exp to the value of x. And that should calculate this for us. Right? So let's just make sure that this calculates things accordingly. Oh, we forgot, we deleted our x, right? So float x. Great. So let's plug in 1. That gives us 2.71828. And let's run this just again. Let's type in, say, 7. That gives us a really big number, of course. Now, how accurate are these numbers? Well, that depends on the Taylor series approximations of itself, and we can, fine-tune this in the future, of course, with some mathematical backgrounds. But this is another application of functions, which will calculate the value of e to the x, which is going to be very useful for other things down the road.